Yes. Okay, differentiate the types of the superconductor. Okay, here is the basic, basic comparison I have given, and here how it behaves, and this thing I have given, right? You can write this for if they have asked for, some explanation, or they have perfectly differentiation also, that also kind of no worries. But here is the, main thing I can say. Oh, wait. I'll explain first this thing. Yeah, below the for type 1 superconductors, I can say type 1 superconductors, below the critical field it behaves as the perfect diamagnetic. Means what critical field, what it is having, the superconductor is normal state and superconducting phase we are having, if the external magnetic field increases beyond the HC. Okay, HC, that is the superconducting specimen give converted to the normal state. They converted to normal state, and the magnetic flux line, the penetrate in, and the resistance, the increases from 0 to some other values. Okay, and as the critical field, they are low, and the type 1 superconductor, they are not used for the concentration of the solenoids and superconducting magnets. One of the part of the application. Below the critical field, diamagnetic. External field increases beyond the HC and gets converted into the normal state, and magnetic flux and penetrate and increase in the 0 from to some other value. That is type 1 superconductor. And here we are having the thing. Okay, intensity, magnetization, HC. We are having a superconducting phase and normal state. What happens? So here's the diagrammatic mean. We can say representation, how it's the graph is going on. Okay, here the other case, they are having two critical field Hc1 and Hc2. For the fields less than Hc1, what happens? It expels the magnetic field. Less than the Hc1, we are having two fields here, Hc1 and Hc2, and for the less than, expels the magnetic field completely and becomes perfect diamagnetic. And between Hc1 and Hc2, flux start penetrating through the specimen, right? It's, and then what happens? The state called vortex state between those Hc1 and Hc2. Below, less than Hc1, it becomes the perfect diamagnetic. And next state we are having Hc1 and Hc2, we call vortex state. And Hc2 is 100 times higher than the Hc1. What happens? The flux penetrates completely and becomes normal conductor. It becomes the normal conductor. Okay, Hc1, Hc2, and here vortex state I can say, and no flux penetration. Here the flux penetration, and here is the normal state. Okay, type 2 are the manufacturing of the superconducting magnets of the high magnetic fields above 10 Tesla. So again, here I'll give the, after giving the brief of this, I can compare this thing. The transition from conducting state to normal state in the presence of the magnetic field sharply are characterized by the critical magnetic field Hc1 and Hc2, and there are these are the elements in the pure form. These are elements in the impure form of alloys or the compounds, and the value of Hc is very small, and here the Hc1 is small, but the Hc2 is very large. We can say 100 times greater than the Hc1. They exhibit complete Meissner effect up to Hc. Meissner effect up to Hc1. At Hc1 penetration start, the flux penetration completes. At Hc2, the material becomes normal. And then the superconductivity observed up to critical magnetic field Hc. Here zero resistivity continues till the field reaches to Hc2. Applications are limited. Here we have wide range of applications. Write this diagram here. It's very important. Like if you write, you'll get very good impression on your paper.